Welcome everyone and good afternoon. I'm Dr. Cecilia Mattevi from Imperial College London, and it is my great pleasure to welcome you all to the joint symposium between Imperial College, King's College and UCL on 2D materials. Today, the program will give us a flavor of the ongoing research in 2D materials within these three different institutions. And the speakers encompass material scientists, chemists, physicists, and engineers. Indeed, the program reflects the largely multidisciplinary nature of the field of 2D materials, which is quite remarkable considering everything starting from one two-dimensional material, graphene, about 15 years ago. And now we count many different 2D materials from chalcogenides to oxides and more. And the field has expanded from being mainly the domain of physicists to become a truly multidisciplinary area of research. But now is the time to give the floor to the speakers. And our first speaker is Dr. Felice Torrisi from Imperial College London. And Felice will tell us about inkjet printing, I believe. But I leave Felice the time and the opportunity to, to read his talk, his title. Okay, over to you, Felice.
Thank you, Cecilia. Yes, indeed. If you can see my slide now. Yes, indeed. I'm going to talk about some recent results we had on printed electronics with two-dimensional materials. So first of all, thank you very much for giving me the opportunity to present these results of the symposium. It's really a pleasure for me to be able to update the LCN with these results. So essentially, I'm going to focus on an aspect that is pretty relevant at the moment. It's still connected to flexible electronics. So of course, there's been a decades of development in flexible electronics, and there's been really state-of-the-art materials that can outperform, for example, previous results of decades ago. You know, the state-of-the-art of, for example, flexible touchscreen displays or even flexible energy systems have achieved really a state where, you know, they can really make a difference, particularly on conformable systems or systems that are not really planar. Of course, the area of flexible electronics has extended beyond the more standard devices into, for example, new areas like sorry, just getting the pointer right. So the area of smart textiles and wearable electronics. And I think that's the area where, you know, the current state of the art of flexible electronics needs to be improved. So people, for example, have tried, this is a work that we did a few years ago, have tried to actually make wearable devices with flexible systems. But that was done just by rolling, for example, a flexible system around the wrist. But that's not really what we mean by wearable, isn't it? So we need to bear in mind that wearability, I'll show next slide, needs a little bit more of that. And also these devices require very stringent features: low power for portable devices, high mobility, when I say high, around 20 centimeters square per second, high on-off ratio, and also flexibility. And particularly, we need to remember that most of these devices, particularly, you know, to work as a backplane in TFT displays, they need to really work with either CMOS logic or PMOS logic to create circuits that could be complementary, working together at the same time. Wearable devices instead require a bit more than just being flexible. You need more stretchability than what you get with flexible devices. You need to have conformability, breathability because of skin contact, and also integration with clothes, as well as washability if you need to, for example, reuse these devices several times. And also if we're looking at applications and long-term environmental stability. And as you can imagine, some of the materials used at the moment in flexible electronics can't really be you know, washable and stable for a longer time than what is needed. So on top of that, we need to remember that ideally we want to fabricate these devices in a large area. So the current printing techniques, of course, are still valid. They need to be used. And for example, inkjet printing, screen printing, flexographic, and spray can definitely be considered, as a key enabling techniques for large-scale manufacturing. In particular, inkjet printing is extremely important together with spray because they can be a non-contact mode. And this is very important where we're moving from flexible substrates that are flat to actually non-flat or non-planar substrates. Case, for example, we are looking at techniques like inkjet printing or spray coating that could deposit materials and pattern at the same time. On the other hand, we need new materials that can outperform in the area of wearable and washable, where the current materials cannot really compete. So what we try to do, we try to explore layered materials that really offer a platform already for conducting or semi-metal materials, semiconducting materials like transition metal dichalcogenides or metal oxides, and wide bandgap semiconductors like boron nitride. It could be used as an insulator and so on. And we try to see whether these could be actually useful as active materials for wearable electronics and also optoelectronics with printing time on 2Ds. But if we look at the properties of graphene, of course, we know that being an atomically thin material is highly transparent. Also, with some doping and improvement of the stability of the material, you can achieve sheet resistance down to few tenths of ohms per square. And this is pretty relevant for conductivity of consistency of conductivity in conducting tracks. And also, it's a pretty stretchable unit. And this is very important when you want to make stretchable, highly conformable devices. And most recently, the compatibility essentially of these 2D materials with skin or with different type of tissue has been heavily explored also due to the pandemic. There's been very recent papers actually really highlighting the strength of some of these 2D materials in contact with biological environment. And this is very important for wearability, as I said. So what we try to do, we try to use liquid phase exfoliation, try to exfoliate layered materials in solution via various types of shear forces, which I'm not going to really thoroughly investigate and show you today. But with this, we can actually really create dispersions of high quality 2D materials. Of course, we need to go from a standard dispersion into an ink if you really want to develop printed electronics. So first of all, we check the quality of these flakes, and it's very well known that, for example, for graphene inks, shear exfoliation allows to have high crystallinity with low structural defects. Indeed, there is no in-plane defects in, for example, in graphene flakes, as you can see from Raman, and actually high resolution TM confirms the same. So we can have a very reliable and robust exfoliation technique to make these inks. And this can be done, for example, in a way, to create dispersions with a high concentration. So you can really get concentrations up to tens of grams per liter, for example, with graphene. But then if we take these inks, and we, for example, bar-coated on a single PET substrate, which is standard flexible substrates, you can, yes, make flexible, nice flexible transparent conducting films as a result of an interconnected network. But if you look at the data in literature, there is a very broad range of conductivity at the moment. And it's really very difficult to have consistency sometimes with these films, particularly in the last year. So we try to work a lot, for example, in the area of printed electronics, focusing on inkjet printing and trying to optimize every step to try and control really the quality of printed patterns and try to get reliable printing. So in inkjet printing, as you know, we normally start from a cartridge, which is made of several nozzles. So the problem with the nozzle is that it has a defined diameter. So whenever we want to print through this nozzle, we really need to optimize our materials dispersed in it. So we normally look at flake size or nanoparticles if we're looking at nanomaterial size. It is around 20 times smaller than the nozzle size. And then there is a strong work on the tunability of viscosity, surface tension, and density of this material so that you can really get a so-called drop on demand. That, for example, we optimized printing techniques to make sure that we have single drop ejection from a nozzle. So this is, for example, an optimized inkjet printed graphene ink. And if you get drop on demand, you can control the volume. So by controlling the volume, you can even get very nice and thin films that, for example, can work as a transparent conductors. So if we try and investigate what these look like, they really look like networks of large flakes. And of course, in this case, percolation rules. So we need to consider that here the conductivity below a certain percolation threshold is dependent on the thickness. And particularly, you start having a linear dependence of the conductivity as a function of the thickness. This is a cross-section of a thin film above a certain critical percolation threshold, which we call TC. So you have a linear behavior, essentially, of the conductivity until it reaches a certain percolation here, percolation threshold with a minimum thickness, where you have a bulk-like behavior, so a constant behavior of the conductivity. Of course, we try to understand a bit better this to try and also describe what's happening and improve our devices. So one of the figures of merit in thin film technology is transmittance over sheet resistance. This is very well described by the thin film limit equation, where you consider the transmittance due to the optical conductance and the impedance of the free space. And if we couple this with the sheet resistance, you can get this nice feature where you have transmittance sheet resistance, and then you have a ratio of actually two figures of merit. One is the conductivity in the optical conductance and the conductivity in DC. Now, normally these two parameters are constant for a material, but because the conductivity, as I told you, deviates from standard bulk-like behavior, and we can see this experimentally. These dashed lines would be what a graphene single sheet would look like, and that's what happens with our flakes. So the conductivity, we know that above the percolation threshold, when T is much larger than TC, actually corresponds to this equation here, where the bulk conductivity is modulated by the ratio between the thickness and the minimum thickness. So we can also modulate the transmittance with a new figure of merit that we call percolating thin films figure of merit, where this is actually described. So by doing this, essentially, we could optimize our printed devices. We can get very nice devices. We can look at the mobility of graphene transistors. And you can see it's very high here. And also we can look at the transport. So in this case, it's a three-dimensional behavior. I'm trying to go quickly. But particularly, this enabled us to print transistors. And in this case, these are fully printed devices using graphene and boron nitride, here with a mobility of up to 150 centimeters square volt per second. The problem at the sticky point, as I said, is the fact that the mobility is very low. So even if we try to make flexible devices, this really, we need to look for new materials. Of course, we can also make these transistors on textiles. So this, of course, shows, for example, washability for these devices. But of course, we need to go beyond standard devices made with graphene, which are limited in terms of mobility and also are limited in terms of the output devices that you can get. Here you can say, for example, an OR gate that is actually following the two inputs, A and B, and the output is actually giving the OR gate truth stable. However, the device is very slow, and this is also due to the very poor on-off ratio of the device. So we start looking at other two-dimensional materials. As we know, there is a large range of two-dimensional materials, and this can be exfoliated by LPE. But the problem here is that the thickness is very high. So you really can't get nice devices that can be nicely modulated. They are too thick, they are highly resistive, and there is a lot of reports that have been shown that the only way to get some modulation is by ionic liquid gate modulation. So that's not really good. You get a kind of electrochemical cell, which is not even stable. So what we try to do here, we try to use a recent electrochemical exfoliation process that uses, for example, an intercalation with quaternary ammonium molecules. In this case, it's tetraheptylammonium bromide. And actually, MoS2 crystals can be nicely exfoliated by intercalation, and then a mild sonication to get a large concentration of MoS2 inks that you can deposit on a substrate. So we try to follow this process, get highly concentrated MoS2 ink, which surprisingly gives much better flakes. In this case, we have flakes of really 1 nanometer picked at 1.7, so really, really few layers, which are also pretty large, half a micron roughly, but with peaks of even 1.2 microns. So that's exactly what we want to get a more reliable feature for printed devices. Then we worked on improving the printability with, again, the tricks I showed you earlier on, so surface tension and density. And then we try to print devices. In this case, we have fully printed MoS2 FETs. And here we can see the MoS2 flakes bridging source and drain. And then we take a look at the morphology of the gate. We see that it's uniformly covering source, drain, and gate. That's exactly what we want, to have a uniform conductivity between source and drain. And also, thanks to conductive AFM, we can actually check what percentage of this channel is actually conducting. So here we're really looking at the conducting path between source and drain. So we will work out around 75% of the actual channel it's conducting. And then this combined to the morphological uniformity actually allows us to have very nice FETs that are modulating, showing a typical N-type behavior of MoS2. Here you can see that, with relatively small VGS, we can modulate the ID. And also we can see that the conductivity, the resistivity is actually modulated thanks to VGS with the typical FET behavior. So this is extremely interesting because we can also extend to integrated devices, fully printed integrated devices, by printing many FETs in sequence. So for example, here you are seeing two FETs working together, showing a mobility of around 0.5 centimeters square volt per second, which is actually underestimated a little bit because of the contact resistance that is pretty high in these devices. So we believe that this could be around few centimeters square volt per second. But the important point here is the on-off ratio. This is much higher than graphene, and is actually moving towards what you really need for printed devices and printed and wearable devices. And here you can see, for example, the inverter working, fully printed inverter, interconnecting two MoS2 devices, giving us a gain of around 4, which is actually, of course, way better than what we were getting with graphene. So we can definitely amplify the signal. And then we can also combine this technology, the MoS2 printed technology, with organic electronics printed devices. In this case, we are showing compatibility of hybrid devices with existing organic systems and 2D material systems. So this gives us, for example, inverter designs with very fast response. We're looking at around 3.3 microseconds. In the case of graphene, we were, for example, we were getting up to even milliseconds. So these devices is much faster than what we obtained previously. And also we can see that there is still an amplification of the signal, even working in AC. So this essentially is the first demonstration of a working pattern between 2D materials printed electronics and organic printed electronics, trying to see where 2D materials can actually improve in some of the, for example, the limitation and the weakness of those ones. And of course, what we believe is that, first of all, the 2D material inks could be a viable platform to work together also with existing organic electronics for wearable applications. And the key point is the understanding of the electronic transport to try and explain how these devices work, and also see whether the electronic properties could be optimized for printing processes. We also demonstrated that it is possible to make fully printed 2D materials semiconducting inks that work in printed devices. And particularly, this could really open up a way towards printed systems, fully integrated with other 2D materials or also with organic electronics. So trying to really create a hybrid platform that could outperform the already existing limitations. Yeah, and with this, I hope you heard all the talk this time. I want to acknowledge my collaborators at Imperial, a lot of people at Cambridge, at Jannan University, Politecnico di Milano, Sucio, and Technion.
We really need to wrap up. Thank you very much, Felice, for the very interesting talk. Okay, so we will move on with the next speaker. And then when Felice will be back, we will see his talk, or the final part of his talk. Okay, so we welcome now Dr. Noelia Rubio Carrero from Imperial College London, and she will tell us about charged graphene as a versatile precursors for multifunctional grafting.
Thank you, Cecilia.
Over to you.
Yeah. I hope everyone can see my slides. Yeah, so as Cecilia mentioned, so I'm going to give an overview about how charged graphenes can be used for different types of applications through multifunctional grafting. So they use there are different techniques to nanomaterials and make them more compatible with solvents in order to use them in different applications. So one of these techniques is reductive chemistry to prepare this to individualize nanomaterials and improve the processing. So we move from I'll put the pointer from to zero-dimensional materials such as fullerenes. They have been charged using potassium in ammonia, then move to one-dimensional materials such as carbon nanotubes, and eventually we move onto the materials such as graphene, which is the topic I'm going to explore here. So in our work, we use a mixture of solvent on sodium and naphthalene and a specific solvent, either THF or dimethyl acetamide. to exfoliate graphites. So the sodium intercalates between of the layers, and the negative charges repel these layers. So they separate electrostatically. And we can use these negative charges to react with a specific molecule. And so this way we can customize the final graphene. We can add specific functional groups if we want to prepare maybe graphenes compatible with composites in bio applications or in fuel cells. So in one of the works that we have studied, so we efficiently charge these graphites, and then we use different approaches to produce polymer functionalized graphenes with polymethyl methacrylate, which is a good polymer to make graphenes more compatible with epoxy resins for application in composites. So we explore graphene-2 approach, where we previously synthesized the polymer and then grafted on the graphene layer. Or we used the monomer. We added directly the monomer to the charred graphenes in a graphene-from approach, growing the polymer directly on the graphenes. So focusing on the graphene-from approach, where we add the monomer and then we grow the polymer on the surface. So we were able to customize the final polymer in terms of molecular weight. And we studied the different functionalities using TGA. So from TGA, we are able to estimate the amount of polymer from the degradation of between 300 and 600. So from this degradation, we can calculate how much polymer we are attaching on the surface of graphene. So as we increase the molecular weight of the polymer, we observe a higher mass loss. So Raman spectroscopy also gave us also confirmed that we were functionalizing the graphene with this polymer. We focus on the D band, which is indicative of defects. So from these to G's ratios, we observe from this graph, as we increase the molecular weight of the polymer, we observe an increase in the D to G ratio, meaning that we are introducing defects on the graphene layer from these polymers on the structure. And from looking at the 2D to G ratios, so this ratio will give us an indication of exfoliation. So as the ratio increases, as the D to D band increases, we observe an increase in exfoliation. So we also were able to see that as we increase the polymer molecular weight, we observe an increase in the 2D to G ratio, meaning a better exfoliation, probably because this chain are separating the graphene layers more efficiently. Looking at the, we previously synthesized the polymer and then attached directly on the graphene. In general, we were seeing lower mass loss values, meaning that we were not able to attach such a big amount of PMMA as with the previous approach. And from the Raman experiments, from the D2G ratio, we didn't observe a very big significant risk difference between different molecular weights. Probably, as we can see from TGA, we are having more or less similar amount of polymer grafted on the surface. We were able to characterize these functionalized graphenes using AFM. From this, if we compare the starting material compared to just exfoliated and functionalized with PMMA, we observe from the AFM how the height of the starting material is around 30 nanometers for this stack of layers. And after exfoliation and functionalization, we were able to decrease this height of aggregates down to 4 to 5 nanometers. In this graph is a good summary of both approaches and how they compare to each other. So we can observe how as the grafting ratio versus the polymer molecular weight. For the grafting-from approach, as we grow the polymer on the surface, we observe an increase in the grafting ratio as we increase the polymer molecular weight. And on the other hand, in the grafting-2 approach, we observe the opposite trend. We observe a decrease in the grafting ratio as we increase the molecular weight, probably due to a higher steric hindrance of larger polymer molecular weights. And similar in terms of dispersibility, as we increase, we are comparing dispersibility in acetone versus grafting ratio. As we increase the grafting ratio, and for the grafting prone approach in red, we observe an increase in the dispersibility. We are increasing the amount of PMMA on the surface, so the layers are separating more and getting more and better dispersibility. They are dispersing. In the case of the grafting 2 approach, the 3 samples were not significantly different in this case. So we use these materials. The final aim of this material is mixed with an epoxy resin and use them in composites. So if we observe under the microscope how is the dispersibility of the materials in this epoxy. So when we added the graphite starting material to epoxy, we observed the presence of big aggregates, meaning that it's not very well, it's not very compatible. And when we added exfoliated graphene, this aggregate became much smaller, and even more when we use the PMMA functionalized graphenes, and also with a higher molecular weight, we achieve a very good dispersibility in this epoxy resin, which will be good for further applications. In a different approach, so we were able also to produce another precursor. As we obtain these graphenites, we are able to brominate these layers using bromine. So we are able to obtain this intermediate that can be later functionalized with different functional groups. So we characterize this brominated graphene using XPS. From the bromine component, we are able to confirm that we have the presence of bromine covalently attached to graphene. And this intermediate is very useful to carry out all sorts of chemical functionalizations of graphene. So we are able to grow a polymer on the surface. In this case, we chose a methyl methacrylate, similar to before, because we wanted to see the compatibility with epoxy resins. But we can use any other monomer that can go through atom transfer radical polymerization. And also we are able to substitute these bromine functional groups with another molecule, which can be, in this case, a polyethylene glycol polymer, which can be useful for biological applications. But again, these bromines can be substituted with any other functional group of interest. So looking at the characterization using TGA, so from comparing the PMMA functional graphene and pegylated graphenes. So after carrying out, this is the TGA of brominated graphene, after carrying out the polymerization with PMMA, we observe an increase in the mass loss, meaning that we are introducing these PMMA chains, and confirm also with the fragments from mass spectroscopy from the fragments of the polymer. And something similar we observe with when we synthesize the pegylated graphenes. We observe an increase in the mass loss compared to the brominated ones, and with the fragments at 15 and 31 corresponding to the pegylated PEG chain. So this dispersibility, the solubility of these graphenes improve significantly compared to the starting material, and in acetone and ethanol after today's sedimentation, which is good for further applications again. So these pegylated graphenes can be efficiently used as nucleants for 3D protein crystals. So these different carbon nanomaterials have been pegylated in this work using graphenes and as flat structures, cylindrical structures such as multi-wall or single wall, or spherical nanostructures such as carbon black. So the best nucleation the best nucleant for 3D protein crystals that we observed was the graphenes that contain this pegylated this PEG chain. So in a different work, we have also functionalized different graphene sizes, as the functionalization is inherent of the starting material. So the choice of starting material is something very important, and sometimes it's not very well addressed in research work. So it's useful to see what's happening as we decrease and as we carry out the functionalization, and we decrease the size of the layers. So we use graphites ranging from 61 micrometers down to 100 nanometers. And we charge them smaller and larger flakes. We charge them with sodium naphthalite, and then we were able to functionalize with this bipyridine molecule that can complex platinum atoms. So in this way, we are introducing a molecule that can complex these platinum atoms, and we will be able to see these platinum atoms in a scanning transmission microscopy. So so we were able in this graph, we were able to see how the grafting ratio changes according to the flake radius. So if we look at the blue trend, as we for smaller flakes in the range of hundreds of nanometers, we obtain moderately high grafting ratios, and these ratios decrease as we move on to higher flake radius. From scanning transmission electron microscopy, we look at three different graphite sizes: small graphenes around 600 nanometers, medium-sized graphenes 35 micrometers, and much larger graphenes around 60 micrometers. So we were able to see these platinum atoms from the different samples. So for the smaller graphenes, we can see how the platinum atoms are uniformly homogeneously distributed across the graphene layers. And on the other hand, for our medium graphites, we were able to see the platinum more concentrated around the edges. And for larger graphites, they were more concentrated, forming clusters or agglomerates, which it fits our theory that the functionalization is initiated by pre-existing defects or also edges. That's why we see them in this case, medium graphites more concentrated around the edge. And finally, in a different work that I'm carrying out at the moment, so we are using these graphenes to prepare electrodes for fuel cells. So the idea is to traditional electrode for fuel cells. They use platinum deposited of amorphous carbon. So the idea is to use alternative materials that can decrease the amount of platinum, and also these new materials can improve the performance of these electrodes. So the idea is to use the same method that I described before, charging graphites to produce graphenites, and then we can use a platinum source that will reduce in situ to produce graphenes that contain these platinum nanoparticles, which are the catalysts carrying out the oxidant reaction in fuel cells. So we are able to scale up this process using reactors available at Cecilia's group. And in this way, we can prepare an ink that will be, sorry, see if I can. That will be later sprayed using this same machine, as we can see in this video. So once we hand the ink, we can produce membrane electrode assemblies in the range of 1,000 square centimeters in size, and we can scale it up as to 5,000 square centimeters per week using 8 grams of electrocatalysts. So they will be the electrodes to prepare the membrane electrode assembly. So these MEAs, as we call them, so they can be stacked together, forming a demonstrator. And we have compared the performance of a graphene-based MEA here in blue compared to a commercial platinum on carbon. So we have studied the carbon corrosion over 5,000 cycles. So for the commercial platinum on carbon, even though it has an initial better performance, but it lost 45% of the performance after the 5,000 cycles, compared with the graphene-based MEA, which only lost 15% of the performance, which is promising, and it can be further optimized. So as a conclusion, we can use different techniques from these graphenites to prepare different functionalized graphenes that can be used in different applications. So we have from these graphenites, we have prepared PMMA functionalized graphenes that have proved to be compatible with epoxy resins, and we can further use them in composites. We have been able to prepare brominated graphene as a precursor to prepare again, PMMA functional graphenes, but it can be any other, we can add any other type of monomer. And also we have prepared some pegylated graphenes that can be used as protein nucleants. And from these graphenites, we can also add a platinum source that can to prepare platinum nanoparticles deposited on graphenes, which are useful which have improved to be useful for electrodes in fuel cells. So just to end with acknowledgements, thank you to Milo, Schaffer, and Cecilia for the supervision, and also the rest of the all NanoHub group, which have been proved to be not only good in work environment, but also in personal life, and also to funding APSRC and Graphene Flagship, and all of you for your kind attention. Thank you.
Thank you very much, Noelia, for the very nice and very interesting talk. Time for questions. Questions from the audience? Well, I will start with a question. So you have shown this very nice functionalization of graphene platelets to be embedded into polymeric matrices. Have you had the chance to characterize some of the properties of these epoxy resins now, let's say, functionalized with graphene?
So we are actually looking at with someone, another PhD from our lab, Johan. So we are trying to have a better understanding about the distribution of the graphenes on the epoxy resin at the moment, and the idea is to do some mechanical tests as well on them. So yeah, we are doing that at the moment.
Okay, so any permeability or conductivity?
Yeah, also conductivity as well. Yeah, sure.
Okay. That's interesting. Well, as I don't see other questions upcoming, what do you envision to be a very interesting functionalization of the different type of graphites that you have shown functionalized with platinum particles? So what do you envision to be the next step in functionalization of graphite platelets?
You mean which field or?
Yes, where do you think is the next step in after this demonstration of the dynamics of formation of platinum functionalization?
Well, I guess it depends. Like I think it depends on depending on the final application. So it will be having knowing how each graphite behaves is important to know what to choose and customize it for final application. Maybe smaller graphenes will be better to functionalize with PMMA with polymer chain that will be more. It will be easier to disperse in a polymeric matrices. And maybe larger graphites is better to use them as maybe to deposit on surfaces for biosensing. Maybe they are well exfoliated. So I think it's having a well understanding of the material, the starting material, and how it behaves is important for the final application. Not sure if I'm answering your question.
Yeah, that's very interesting point, and I guess also in some application where you want to have preferential age functionalization rather than a uniform functionalization across the plane.
Yeah, definitely for larger graphites, it will be more distributed around the edges compared to smaller graphenes, which will be more homogeneously distributed. So yeah, it will have a chance to customize what we can do or what we want to achieve eventually.
Okay, great. Thank you very much, Noelia.
Thank you.
Any questions from the audience?
I think Sandrine has a question.
Just unmute. Yeah, sorry. Sandrine, please.
Hi. Yeah, thanks very much. Really interesting talk. I was on those charged flakes. So presumably you can tune the density of charging. But I was wondering if you can if you can form like a lattice of charges on those flakes at all.
You mean to know? You mean different
structures of where you know if you can localize the charges and if you can form some.
Yeah, well, depending on the precursor that we're using, we could maybe have one layered charge, or maybe two layers intercalated with sodium, and then two layers of graphite, and so on. So they're called stage graphites. So we can, I mean, with this maybe we're using charging with potassium. Maybe we have a better we can customize it better to know. Maybe we can have different two layers charged with graphene, and then two layers not charged, and then two layers charged, and so on, like in a stage way. So there's a way to customize it. Yeah.
Okay, that sounds really interesting as a building block. Okay, thank you.
Thank you.
Okay, I don't see other hands raised, so I think we will move on to the next speaker. Thank you very much, Noelia.
Thank you.
So our next speaker is Dr. Antonio Lombardo from UCL, and he will tell us about 2D materials for heterostructures and miniaturized microwave biosensors. Over to you, Antonio.
Thank you very much, Cecilia. Thank you very much for the opportunity. I'm going to share my screen. Okay, can you see it?
Yes, I can see it. Thank you.
Excellent. Thank you very much again, Cecilia. So I just would like to quickly introduce two different areas of research we are investigating in our group. The first will be heterostructures based on two-dimensional materials, and the second will be about the use of graphene for microwave biosensors. So let's start from the heterostructures. So heterostructures have a very major role in modern technology. We can just think about high electron mobility transistors or semiconductor lasers. And to me, as a device person, two-dimensional materials, which are very interesting as they are, becoming even more interesting when we combine them together. And because these materials have saturated bond on the surface, and typically they are held together by van der Waals interaction, we can combine them in any sort of order and also angle without the constraint that we normally have in three-dimensional materials. And that one, this property result in a really incredible flexibility. First of all, because the family of two-dimensional material is very large. We have a lot of materials to choose from, and we can combine them in whichever order and whichever angle. When we started working in heterostructure, the very first problem we had to face was the fact that when we combine different materials, impurities and contamination get trapped at the interface, and they form the so-called bubbles and blisters. So in any heterostructure, the device is at the interface. So we really had to make sure that the interface was of the highest possible quality. So the first problem we were trying to face is how it's possible to sort of clean the interface. So we developed a method in order to manipulate the blister. So unlikely other methods that were available before, we decided to not to care too much about the formation of the blisters when we assemble the heterostructure, and rather focus on how we can eliminate the blister once the full heterostructure is formed. So we developed this method which combines two factors. It combines the temperature and the sort of mechanical push. So the method works as follows. Let me open the laser pointer. So this is an example of a heterostructure consisting of graphene encapsulated between two layers of HBN. And this on it's not on a substrate, it's on a polymeric stamp. As we laminate the heterostructure onto the final substrate, then we combine the effect of temperature, which makes, first of all, the stamp, which is a polycarbonate stamp. When we bring the stamp above the glass transition temperature, it becomes sort of at the point that when it starts to become fluid. So that factor combined with a sort of gentle push on the side allows us to have a contact front that moves along the heterostructure. And that's the contact front moves, as you can see in the second picture. It collects all the impurities which eventually are merging together and they're pushed out of the heterostructure. So at the end of the process, we end up with a sample which is completely clean of impurities. And you can see, if you look close on the AFM picture, that there are some impurities just at the edge, because when there is a discontinuity, that acts as a sort of a pinning point. But the entire graphene area is completely free of blister. So in other words, we are achieving atomically clean interfaces, but we also are limited only by the sample size. And that is very important when we do devices. Obviously, we developed the method for graphene at HPN heterostructures, but it's also very important to apply for other materials. Indeed, we are nowadays working quite a lot with transition metal chalcogenides, and the method works also for this kind of structures. We also wanted to push the method further, so we intentionally contaminated the surface of graphene. So we exposed graphene to all the things that normally graphene is exposed to during fabrication. So we spin-coated PMMA, we used organic solvents, developed all these kind of things. And even in this heavily contaminated sample, we were able to apply the method and essentially have practically the entire surface of graphene clean of blisters. We characterize the interface of the graphene boron nitride, the boron nitride graphene boron nitride heterostructure by Raman spectroscopy, and more importantly by transport. So Raman spectroscopy reveals that the defect level is very small, as we would expect in exfoliated samples. We see a very large 2D over G ratio. And if we map all the Raman parameters, such as the full width of maximum, the position of the peaks, and the ratio, we see that the variability is very small. We are very much within the resolution of the instrument. So we are talking about 1 centimeter to the -1 as maximum variation. We also investigated the transport. So eventually we are a device group. So for us, transport is the goal of our research. So by integrating the heterostructure into all bar, we were able to identify independently conductivity and mobility. So you can see in this picture that if we plot the resistivity, we have the typical graphene peak in the proximity of the charge neutrality point. The charge neutrality point is located at a very small gate voltage. Consider these samples are backgated using a 300 nanometer silicon dioxide. So 0.2 volt really means a very high intrinsic device. We also measure the mobility as a function of the charge carrier concentration in the presence of moderate magnetic field. And we achieved very high mobility at room temperature in the order of 180,000 centimeter square for a volt second. And this mobility, as expected, was going much higher at low temperature, where approaches about 2 millions. And what is also important is the disorder-induced charge inhomogeneity was very much similar to suspended samples. We also wanted to check the reproducibility of these results. So we fabricated a number of devices, and we have seen that, first of all, there was very good consistency between different samples. So we had an average 160,000 across all the devices we fabricated. And what is probably even more important, we couldn't see any difference between samples that were clean to start with or clean that we have intentionally contaminated and then cleaned. And so overall, the results were very much comparable with theoretically predicted limit due to electron photon scattering. And from a technological point of view, it's important to note that the mobility remains high even at larger charge carrier density. So we can go up to about 4 to 10 to the 12 and still have mobility which is in excess of 10,000 at room temperature. And making room temperature also means it's really suitable for real applications. And indeed, we applied this high mobility graphene into a device in collaboration with our colleagues in Pisa, in Italy. And we used the graphene encapsulated boron nitride as channel for Terrace detectors. Terrace detectors which work on two different principles. So on one side, there is the photothermoelectric effect. On the other side, there is the plasma wave mediated detection. So we don't have a lot of time to go into details, but the fact that the graphene had such high mobility was the key enabler to reduce significantly the noise equivalent power, so making detectors more sensitive and improve the response time. That is just a quick overview of this work. If you're interested in more detail, I can provide more in the questions. In the second part of the talk, I would like to touch upon biosensors. So two-dimensional materials, being atomically thin materials, are ideal for sensing, because just like we are fighting against the environment when we encapsulate graphene to provide the best possible environment and therefore sort of achieve the best possible properties. On the other side, we can use the fact that the properties of 2D materials are very much modified by the environment in order to do sensors. And indeed, in literature, there are plenty of studies in which graphene has been used for a number of different sensors, gut sensors, biosensors, and several others. In most of the cases, the structure used for these sensors is a chemical FET. So consists of a field effect transistor whose transport properties are modified by the proximity with the material to be sensed. So if you look at this paper, it's one of the recent work on using graphene for COVID detection. You can see that there is a shift in the electrical characteristics, both in the output characteristic and in the transfer characteristic. And based on the modification of the DC characteristics, one can identify the presence or even quantify the material to be sensed. However, we would like to use a different approach which is based on microwaves. So if we consider a microwave waveguide, and in particular a structure called coplanar waveguide, which can be imagined as the planar counterpart of a coaxial cable, when we have a central conductor that carries the signal and two lateral conductors, which are the equivalent of the shielding or in the coaxial cable. When electromagnetic radiation propagates in the waveguide, we have this sort of field distribution. So we have electric field, which is partially inside the substrate and partially outside, and same for the magnetic field. That means that if we place anything on the surface of the waveguide, the electric and magnetic field will feel the presence of this material, and the propagation will be modified. So in other words, by studying the wave propagation in such device, it is possible to get information about the material or the molecule or the cell, or basically whatever we place on top of the waveguide. And that is normally referred as the electric signature. Signature because coplanar waveguides are broadband detectors. So basically what we can do, we can sweep the frequency and see frequency dependent behavior, which we wouldn't see obviously at DC. They can work in a label-free setup. So just by the direct interaction of the electromagnetic field with the material on top, or can be functionalized with suitable markers to improve the specificity. Also, the use of microwaves has a number of advantages. First of all, allows to make the device very small. Second, reduces ionic losses that are normally affecting sensors at a low frequency. And basically, every time we do biosensing, we deal with materials which are dispersed in some solution. So ionic losses are typically quite significant. And last but not least, the power that is delivered through the waveguide is very small. So they are essentially not invasive. So typically, coplanar waveguides, if used for sensors, are integrated together with the microfluidic channel. The microfluidic channel that confines the interaction between the liquid and the propagated wave only in a very small portion of the waveguide. And these are two examples on sort of a large scale and also a very small scale where microwave analysis is done down to a single individual alive biological cell. However, as you can see, these waveguides are essentially made of metal. So the only sensing mechanism is through the fringe of the field, so the portion of the field that extends on top of the waveguide. If we instead use a material such as graphene, we have a second sensing mechanism, because in a material such as graphene, we can control the transmission through the waveguide by essentially the equivalent of a gate, or if you prefer, of a chemical doping. So if we look, for example, a coplanar waveguide where we can tune the position of the Fermi energy by using a suitable gate, we can see that the transmission of the waveguide, summarized by the S21 parameter, goes down as the Fermi energy goes closer to the charge neutrality point, which means we have this kind of loss, reduction of transmittance depending on the gate. Whereas while we are moving on the other side of the transfer characteristic of the GFET, we have an increase of conductivity, and therefore we have an increase of the capacity of the waveguide to transmit the radiation. So basically, we have a quite significant variation in terms of the amount of electromagnetic wave that goes through to the waveguide. And on top of that, waveguides are very good structure to identify properties in an accurate way, like we did in this work, where we investigated the RF and microwave conductivity of graphene using waveguides, because they allow a very precise de-embedding of properties. So long story short, that's our sensor design. So we start with atomically material, typically graphene, on a suitable surface. We deposit metal to form a coplanar waveguide, and then we realize a microfluidic channel. So we have fluid flowing along the microfluidic channel, and perpendicularly we let a microwave signal to propagate. The first material that we are investigating is DNA, because DNA really allows us a very good control. So from an engineering point of view, it's a wonderful biological material. And so we functionalize the graphene surface using P-base, which allows non-covalent functionalization. That's the very typical procedure used in many graphene-based biosensors. Then we immobilize a sequence of DNA. It's a complementary sequence of the sequence we would like to detect. And then once the complementary sequence is introduced, we have DNA hybridization, which results in a charge transfer and therefore a change in the graphene conductivity. So we do that, and we study the transmission from the kilohertz up to about 50 gigahertz. We acquire data using vector network analyzer and scattering parameters. You can see the setup. So here we have the array, we have the gate, which I would more correctly call counter electrode. That's the microfluidic in and out, and these are the two RF probes. And basically acquiring the scattering parameters at different deposition. So after the deposition of the probe, after the deposition of the probe in the presence of the buffer solution, and finally having probe and target DNA, which means that the sequence we want to identify, we can measure the real and imaginary part of the waveguide impedance. So we can see that there are quite significant changes the moment we introduce the target sequence. So we have change in the real and as well as the imaginary part. And we also, having been forced for a while to be away from the lab, we also thought a little bit outside of the box. So the scattering parameters are not really a direct measurement of material properties. So we thought, what if we apply machine learning to extract the information directly from the scattering parameters? So what if we sort of get rid of all the modeling and we just focusing on the raw data as they come from the machine? So we use electromagnetic simulation to produce data for a large number of devices. And then we applied machine learning, assuming that we wanted to test glucose model using a call model. And we can see that basically we have a very good agreement between the test data and the data we have used to train the system. And it's a very simple machine learning. It's just a principal component analysis. And we are currently looking more into details about this opportunity. So sorry, I was a couple of minutes over time. So I just would like to move to the acknowledgement. I would like to acknowledge my students, who are the people who really have done the hard work in what I presented. So in particular, David, who has developed the cleaning method that we use for heterostructure, Patrick, and Lorenzo, who have developed the microwave sensors experimentally, and William and Tianui, who have developed the microwave, the machine learning approach for microwave sensing. I also would like to thank all the collaborators, the source of funding, and we also have a PhD scholarship available in the group. So if anyone is interested, please follow the link, which is in the LCN website. Thank you very much.
Great. Thank you very much, Antonio, for the very nice talk. And time for questions. Questions. I'm trying to see.
I have a question. I tried to raise my hand, but I'm not sure if anyone's watching.
I can see now. Yeah. Please go ahead, Jan.
Okay, what was the question? Oh, yes, just side-by-side comparison. Is it expected that the microwave format of sensor would be inherently more sensitive than the chem FET, or are they really not to be compared at all? Is there reason to think it will win over the chem FET?
That's what we are investigating right now. So what I didn't show is that together with the microwave sensing, we are performing DC sensing at the moment. Our structure allows to do the two things side by side. So we are doing that, and we are actually just finished acquiring all the data. So if you ask me this question in a couple of weeks, I will have a much more scientific answer. But I believe so. I believe that the combination of two together will be certainly better than the chem FET alone. Also because we have another we are looking at the frequency dependent. So we are not just looking at the conductivity change, which is still there, and we see even without having to have the microwaves. But I think what the microwaves add is the frequency space. So what we are doing is we are studying the same device at a different gate bias, and for each gate bias, we are exploring the full frequency range. So we have a sort of two-dimensional parameter space that we can investigate. So I'm pretty sure that we will get more than the simple sort of chem FET.
Thank you.
We have another question from Johannes, please.
Thanks. Thank you, Antonio. This was a very nice talk. I was just wondering, you mentioned that you have this graphene encapsulated by the hexagonal boron nitride. And I was just wondering if you sort of control the alignment between the two, or because then, of course, you can have, you know, this moire pattern and things like mini Dirac cones. I was just wondering if this is something you think about.
Yes, we have all the capabilities to do that. In the particular set of data that I showed, we weren't considering that, but it's something that we can do, and we are looking into it for a number of applications.
Okay, that's very interesting. Yeah, thanks.
No problem.
Thank you. And we have a third question from Franco.
Hi, great talk. I was wondering a little bit along the line asked by Ian Robinson as well, but in terms of selectivity. Just to precise the context a little bit, so if you think to COVID that you also mentioned a couple of times, what kind of selectivity can you make attempt, let's say, risk some predictions on? I mean, would you go down to some viral species, or to even higher selectivity, let's say, distinguish between different variants of the COVID virus, for example?
I think the selectivity comes for a number of reasons. So in the example that I showed, which is to some extent very similar to what has been done for COVID and what has been done for many other materials, really the selectivity doesn't come from the graphene or from the microwaves. The selectivity really comes from the functionalization. And so what we are doing in our DNA experiment, we are mobilizing a known sequence of DNA on the surface of graphene. So that sequence will only bind with the complemented. So what we are really measuring, if you want, is a second order effect, which will be the cascade of the hybridization onto the overall conductivity. I have to say, in the microwave world, people have used metallic waveguides or even more complex structures such as resonators, split ring resonator, and so on, to monitor directly material. Say, for example, it is possible to identify whether a cell is a cancer cell or not a cancer cell, or is it possible to estimate whether you have alcohol or other substances. So in the long term, our goal would be to combine these two effects together. And the ultimate selectivity, I think, will come from the combination of the two.
Okay, great. Thank you very much, Antonio. I have a very, very quick question. I was just wondering whether those type of heterostructure with HBN, you have also explored this heterostructure other 2D materials different from graphene?
Yes, that's what we are doing at the moment. So we are working with a number of TNDs. For example, we are very interested in low power electronics. So we are looking at different kind of tunneling transistors and integration between 2D and 3D materials and this kind of things. So absolutely, yes.
Okay, great. Thank you very